All right. Hello, everyone. So let's start off with some announcements, I think. So the first exam is out, right? I need to fix problem 5. How's everybody's grouping going? So I see that there's probably, let me check on how many people are not in groups right now. This is nothing. Oh, don't do that. Okay, I'm gonna have to look at it later. Yeah, so try to get the grouping. Try to get grouping working. You know, if you're okay, good. Yeah, so basically if you haven't started already, you should start. If you have started but don't have a group, you know, talk to people either on the Discord or something, and then get into groups. If you want a separate channel on the Discord, I can create one for you. So if you want a Discord sub channel, I can create them. Basically, we can give you either text or text and voice. If you want to work together. And basically what we can do is we can just give permission just to your group. So no one else but me and the professors and stuff can see anything about it. So, okay. What else? Oh, right. Project 1 grades were released to me last night, so I will post them. I guess I'll post them after class. And that's basically it in terms of announcements. Okay. Okay, so today I think that we are going to talk more about, am I going to talk about Project 3? Good question. I mean, haven't I been doing that for 2 days? I don't know. I've been talking about skew heaps quite a lot, right? So, let's see. I can do a little bit of, what do you guys want me to say about Project 3? I guess let's go over it again. Oh wait, no, this is Project 1. So, okay. Basically, the entire purpose of this project is a skew heap. And so we've been talking about leftist heaps, right? And we've been talking about skew heaps for about two or 3 days now. So, so you know what the property of a skew heap is, right? So basically it always flips. When you insert to the right, and then you always swap the left and the right nodes on the way back up the insertion path. So, the major operations are insertion, reading, and removing the highest element, blah, blah, blah. So to insert a new element, We treat X as a single node and merge it with H. Question 3 on the exam, is the vector, no, the vector is not sorted. Otherwise, it's just one and what? I guess like list. Right? Okay. So you're going to be creating a PQ class. So let's look at the PQ class. Here's the PQ class. So the first thing you have is this patient class, which is just this, it's basically just a struct with a bunch of setters and getters. Well, really almost just getters. The patient has a bunch of, data. And then you have a node class. Well, I'll post it on Blackboard. So, okay. So then we have a node class. The node class is pretty simple, right? There's not even any parent data, but you don't need any parent data. It's just some public stuff, private left, right. That's it, right? And really, it's just patient left and right. So this is, there's nothing terribly shocking going on there. Okay. And then what else? So here's all the stuff that you have to implement for the project. So basically, get next patient is basically you have to do insert and get next patient. And so those are two things that you have to implement. You are not allowed to make new public methods, but you are allowed to make private declarations. And I think you'll probably, so like for instance, I needed to make a merge function. So this is merged with another queue, but I needed to make a new merge function that merged two nodes. I mean, I guess you could say, well, did you really need to make that function, or could you have just done it with a while loop? The answer is, I don't care, I made a new merge function. Once you make the new merge function, insert, remember how everything in skew heaps works, right? You're merging the two nodes. If this one's bigger than, if this I'm sorry. So I should say here, get next patient extracts it and deletes it. So there's, and then basically, remember how to extract something in a leftist heap or a so how do you extract something in a leftist heap? Basically, if this is the merge function, then pop max is just this, right? And I mean, I'm a little bit, I know I've done this code in class. I didn't mean to code up the project before the project was released. I might upload this to the GitHub, but you have to be careful. You can't just copy paste this code, okay? You have to kind of do it yourself. Also, this code may not 100% work, but because it was coded by me in 20 minutes, so that could be a bad thing. So yeah, basically the whole point here is that the leftist heap, you get the old root, you're going to get the old value, and then you merge the left and the right. Then you delete the old root and return the big value. And here, I don't even have an else. I basically just do if we don't return. If you somehow don't enter the statement, then we just throw the leftist heap empty. In our project, it's actually going to be a domain error where you'll be like, the heap was empty. Don't do that. Or something. right? So, and then merge, like this is actually more complicated than your merge function might end up being. Remember, because here we have to compare MPLs on this one, but you're doing a skew heap, so you always swap. So actually, your merge function should be much simpler than this merge function. Yep. Okay, so what else is there about the project that I should say? Clear, remove all patients from the queue. Yep. So that should be something that you're going to call in the destructor. It's also something you can just call, I guess, if you want to clear out the queue. I don't think it matters terribly if this thing runs in like. Remember, it takes log n time to do a merge. So if you don't clear it like in a traversal, if you clear it in a traversal, it'll take O of n time. If you clear it using the like delete operate, like get next patient operator, while you can get next patient, then it will take n log n time. We're never gonna have I don't think we're gonna have a heap that big to where it's gonna matter. Print patient queue. So remember, this one is a pre-order traversal, and although the first patient will be printed, should have the highest priority. So be careful about this, because I actually looked at the output, and so they say the highest priority here, but well, so the way to think about it is skew heaps, leftist heaps, binary heaps, array heaps, binomial heaps, and Fibonacci heaps are all priority queues. So the way that it usually works is that you have, the way I should say it is like this. And I know that the terminology can be a little bit confusing. So like here is like the idea of a priority queue. And then inside of this, there's a bunch of like, right? So there's like, array heaps, etc. So basically, there's a bunch of different implementations, etc. So that's kind of the way to think about it. So a priority queue is just anything that sets priorities. Where the, let's say the highest priority comes out first. So this is kind of the idea of a priority queue. So if you can come up with a new idea for something like this, even if what you do is, like, here's a priority queue that we haven't talked about. Basically, it's not an array heap. You basically just build an array, and every time you insert a new element, here's an array, and sort it by priority on every insert. And so because the thing is pre-sorted before you can do it, each insertion operation it's actually not O of n log n. You can actually do it in O of n time. On the other hand, it's not great, right? This is possibly one of the worst priority queues you can do. On the other hand, if you know that you're going to have, say, less than 10 elements ever, and you really don't feel like, let's say that you are not allowed to import any libraries or use any queues or any heaps from anything else, then this is a perfectly valid solution to get the top thing. Just keep sorting it, keep sorting it, keep sorting it. But of course, then you're like, you just always have to remember that O of n is going to be here, or technically it could be O of and log n, which might be, you know, bad if n is like bigger than 1,000,000. Anyway, okay, so let's go back to the project. So the number of patients, this one caused me some trouble because I forgot to So remember, if you're going to merge two queues, you have to add the number of patients together. I know that you're going to be like, well, obviously, if you merge the two queues, you should add the number of patients together. Well, I just didn't do that. I forgot to put that stupid addition statement in there, and it caused me about... I think I spent about half the project debugging that particular bug and nothing else. So yeah, don't forget to do the stupid simple things, because if you do, then you're going to spend a heck of a lot of time debugging those things. What else? So here we have a get priority function. So this just returns... So remember what okay, so let's talk about function pointers for just a little bit. So what is a function pointer? Let's talk about function pointers. Let's see. Let's get rid of all this code. Oh, and we don't need the return here. So let's create two different functions. Let's create and let's create another one. I'm doing way too much Python now. So there we go. And so now, you see how these two functions have the same parameters and the same return type. So as it turns out, what C++ understands them as, and you can actually do this, you can say, like, my function, let's say, int Is that how you do it? I forget now. Let's just type def it. Let's say int function. I think that's how you do it. And so now what we can do is declare an int function, and we can just say my function equals square me. And so now what you can do is you can call the function. So let's say int x, cnx, my function on x. And then, sure, let's do while x is not equal to 0. Oh man, I got Python on the brain today. And then we can cnx again. There we go. Okay, so let's see what happens when we do this. I'm sure it's going to completely explode. Okay, it didn't explode. So now let's enter a value. So let's say we enter 5. Hopefully 25 pops out. There we go. 7. Oops. I'm a little afraid of that. 31 maybe, right? So 200 should be like, what, 40,000? Okay, so we see what's happening here, right? So what's happening here is that I've created a variable type. That type is an int function. And so basically it returns an int and it takes an int. I mean, you might call this an int function int or something like that. I don't care what you call it. But the point is that that's what this thing is doing. Okay, let's up this font size just a little bit. And so what you see going on here is that I'm not actually calling the function using the name of the function. I'm calling it using the variable that it's been assigned to. And so the thing is that you can call a function pointer just by, if you have the function pointer, you can just attach like the function parentheses onto it and just feed in an argument, and that will call whatever function that this thing is assigned to. And so that's the same thing as what we have in this priority function business. So when you see pryfn_t, let's find where that's defined. It's defined right here. We see that it's typedef int, so that means it returns an int. Here is a pointer, which just means that this is going to be a function pointer. Here's the variable type, and then constant patient reference. So that just means that these things, a priority function _t, so I'll just call it priority function. This type is a function pointer which takes a constant patient reference. So basically it just eats a patient, and it promises that it won't change it, makes a reference of it. This part you don't really need to worry about so much. On the other hand, the one thing it does do is return an integer. So it's going to return an int that's going to tell you, you know, what the priority of the student is. And so if you think about, so the thing is, in your class, the function is just called priority here. So what you're going to do is actually, you're going to be calling a bunch of, you're not going to be calling like pryfn_t, you're going to be calling priority of some patient. That's what you're going to be doing. Okay? Or alternatively, it's like priority of node, something like this. Right? So if you have a patient, you can call priority on it. I don't know. I think you were supposed to learn this in Computer Science 202. But who knows? Maybe I'm supposed to teach this. In that case, I am teaching this badly. I'm doing this kind of as a last-ditch review of function pointers. Yeah. Oops. So the one advantage of function pointers is that you notice that I can change it here. I can just go, my function is now equal to cube me, like this, and notice that I don't put the parentheses on here. I don't put the parentheses on either one. This is just int function, my function is equal to cube me. Okay. Well, I will, okay, so in that case, let's talk more, let's pretend like I didn't just do this really stupid basic example. So, whoops, that's even stupider. I just hit the escape value. So you notice how 1 is 1, 2 should be 8, 3 should be 27, 4 should be 64, etc. Something like that. So basically the point is here that what's happening is this is a way for you to pass a function as a parameter and then assign it somewhere, and then you can use that function under a different name. And the reason why you might want to do that is because you notice, at least here in the driver code for the project, let's find the driver code for the project. Here it is. There are two priority functions, right? Priority function 1, priority function 2. And you notice that they do different things, right? So this one just returns the triage value. This one returns some kind of more complicated. This is one of the more complicated type of things, right? So basically, it determines the priority based on some set of rules that are, I don't know, like if the oxygen level's too low, or the heart rate's too high, or the heart rate's too high, or the blood pressure's too low, or if the oxygen's, in this range and the heart rates are in this rate is the respiratory rates in this range, and the temperatures in feverish range or less than this. If you're basically an ice cube, then I guess you're priority 2, etc., etc. Keep in mind, so this is the biggest thing to think about for the project, and I guess I could write this in like as large of text as I could possibly write it, so maybe 80 size. This is a min heap project. So that means highest priority equals min. Alright? Yeah. Just keep that in mind. I coded it backwards initially because I read all that stuff about highest priority, and then I had to flip. I think my code was kind of well done enough that I only had to flip one inequality to make it all work. But I thought that, you know, a higher priority would be a higher value, but no. If you're a priority 1, then you are highest priority. If you are priority 2, you are slightly less than highest priority. If you are priority 3, then you're middle priority. If you're priority 4, then you're lower than that, and priority 5, then you're the lowest priority, at least in terms of priority function 1. In terms of the other priority function, the triage, I guess it's also a min, in the sense that, like, if you're triage priority 1, then you are highest priority, etc., all the way down to triage priority 5, okay? So, yes. Let's see if it says that. So, highest, reading the node with the highest priority, highest priority, highest priority. Highest priority, highest priority. Here it is. Must maintain the min heap property. Min heap, right? Min heap, right? So it says min heap all over the place. Well, except for conforming. Yeah, so it supports a min skew heap. If you have 2 priority 1s, good question. So, then whoever's on top, so then it's dictated by the order of insertion and the properties of the skew heap. Okay? So, basically, like, if you have 2 priority 1 people, then one person's already going to be inserted as the root, and then the next person's going to be the right child, but then they'll get flipped to left. And then if you insert another priority 1 person, then they're going to be on the right, and then you'll swap them, and then another person's going to get you right. So that's how equal priority is going to work. So it's just going to... no, because I don't control the document. But I mean, this is, I might even send out a reminder email about this. This thing is a min heap. But yeah, so that's I think that's probably the most important hint that I can give you for this project. And so I think that's, I mean, right? I mean, even I didn't, so let me just admit, this is how I read the project description. I was just like, all right, I skipped this block because I didn't care. I don't think these were up yet, so I looked here. Practice, okay, I'm going to write a heap. All right, learn how to use function pointers. Cool. Recursion, don't care. All right, skew heap. And then I was basically like, I didn't read this. I didn't read this, and I opened these files, and then I just did that. So, let me just say that I want you all to get this project done as quickly as you can, test it as much as you can. I want all of your questions about the projects this week. I don't want you to wait. On the other hand, this project is just not Project 2. Okay? Project 2 was really 2.5 to 3 coding projects put together. Whereas Project 3 is just a 341 data structures project. This is what a 341 data... Well, actually, it's even probably a little bit less than a 341 data. It's like 80%. It's like 0.8 of a true data structures project. Now, I think you guys deserve that after what happened to you last time, so don't get me wrong. But, yeah, so that's the skew heap rule. So you merge the left and the right. And so remember that what happens is if they're both equal... Oh, right. Let me tell you. So it is... I'm sorry, that is indeterminate. Let me tell you what the project requires. Okay. So... Okay. Yeah, so okay. Let me just tell you this up front because this will save you some time and it'll also get you to match the project descriptions. Let's make this a smaller font size. If the priorities are equal, then let me just say this. So let's say if left priority is less than right priority, then what we need to do is we need to merge the left dot right with the right. Else you merge the right dot right with the left. So what that means is that if you have two nodes of equal priority, notice here that this is a strictly less than sign. So at first, I will admit that when I was coding the project, I put an equal sign in here. Because I was like, I'll just do this case first, right? And so your question is like, do I do this case or do I do this case? And the answer is, like, there's no rule in the theory of leftist heaps that tells you which one to do. So I just put the equal sign here thinking, that'll be fine, right? Because otherwise here, technically this is an else if this way, right? So I was just like, well, I'll stick the equal sign on here, but this is wrong. You should stick the equal sign on here or really just make this an else or something like that. So that's how this works. Yeah, so if the left priority is less than the right priority, then you merge the left dot right with the right, and if it's equal to it, then you merge the right dot right with the left. And you notice that I flipped them here, so the left goes on to the right side of this thing, and the right dot right goes here. Now, if you got to play around with it because this is what worked in my code. And so if you write your code slightly differently, you might have to do things slightly differently, but this is generally what I did in order to make it match. And I say that there's, the reason why I'm telling you this is because, why am I saying this? The reason is because skew heaps don't tell you the answer, right? To this question. It could be either way, right? There's no fundamental rule of the universe that says if the equal sign isn't on this one, that just nothing's going to work. And if the equal sign's on this one, then everything is perfect, right? Like, you have a perfectly acceptable skew heap if you put the equal sign here. So, yeah. Okay. All right. So yeah, start writing the project. If you get to this place, then just remember this hint, right? So this is going to be in your merge function. And so when you get to your merge function, then just read this bit of code over after you've finished your merge function, and then see if it works. If your trees are almost right, if they're almost perfect, except they're just a little bit flipped, then just look for this error, because this is what I noticed happened, is that my trees were just slightly off. Anyway, so there's nothing complicated about patient. It's just storing a bunch of ints and like a patient name. Priority function, so this is the this is the thing. This is the function pointer, so pri_t is just the variable type that we're defining as a priority function type. They define these two for you. You can define other priority functions just to try them out, and I suggest you do that for testing. Let's see, what else is there here? There's not really much here, right? Dump is an in-order traversal. Print patient queue is a pre-order traversal. So these are two different traversals that you have to do. The hardest function, I would say, probably is the set priority function. Yeah, because notice here, this is not as easy as just copying the priority function into the old heap. Because the problem is that what can happen is once you evaluate all the nodes on the new priorities, everything can be changed. So this is the hardest function. This is definitely the hardest function. So what I want you to do is get everything else working first, right, with one priority function, and test it out real good so that you know that everything works, and then work on this one. Well, what you have to do here is, my hint to you is that you need to basically build a new heap. Everything needs to be reinserted into the heap. Okay? That's my hint to you. So, like, I did it in a kind of tricky, stupid way, but it is a setter, but it's not just a setter. You have to, this part here cannot be ignored. This part here needs to be bolded, underlined, underlined. I think this is literally half of the how are you getting the nodes? You traverse the old heap, right? So basically, when you set the priority function, you already are going to have a bunch of stuff in your heap, and so what you need to do is you need to pull out the things in from this heap and stick them in a new heap using the new priority function. My hint is that you don't have to. You should use the functions that you've already built here to do it. You can also do a traversal and that kind of stuff, so that's totally within your right, and it's technically a little bit more efficient because instead of being O of n log n, it would be O of n. But anything that's O of n log n, at least for our tests, should be practically indistinguishable from something that's O of n. It's basically a deep copy, except that you have to use the new priority function to rebuild the skew heap, because it's going to give you a different structure, because the priorities of people can change, so people might not just be in the same order. So that's why you have to rebuild the heap, because, like, you know, if we say, okay, like, we're only going to look at resting heart rate or respiratory rate as one priority, then over here we only look at blood pressure, then the priorities of people could change. So this is the one where you have to really be careful. So if the priority function is equal to the previous one, you should do nothing. If the one, and so if it's different, then you should, so basically there's a bunch of safety checking that you should do here. Like if the priority function is the same thing, then you don't have to do anything. If it's a new priority function, meaning its pointer is not equal to the previous pointer, then what you want to do is you want to reevaluate all the priorities of all the nodes and stick them back into the heap. So you're basically, my hint to you is that you should at least have two heaps going on. You should have the old heap and the new heap, and you should do something with that. So private helper functions must be declared. No other modifications are permitted, and so the answer to this is that private helper functions are probably necessary in order to do the merge, so you should do that. You must use a min skew heap. Yep, do that. Priority values may not be pre-computed and stored within the patient in the queue. And so the reason why this is the truth is because of the set priority function thing. Like if you couldn't change the priority function, then this would be completely fine, and this is actually probably the right answer in general, is just to compute the priority and stick it in the node. But also you're not allowed to modify the patient class at all, so like this is like duplicative. Like there's no way for you to actually do this. Insertion to and extraction from the min heap must run an amortized logarithmic time. So basically, this is the only runtime constraint that you have, which is that insertion and extraction. And remember, insertion and extraction are both merge, right? For a leftist heap and a skew heap, they're both running in merge. And so merge is going to be log n, which is this. And so they've given you some operators to output the patient and node objects. I actually didn't use it because I was stupid. I essentially recoded the entire thing. My hint to you is use it, because I didn't even scroll all the way down to see them. They exist. So you can see out a patient node. You can see out a node object. If you see out a node object, it will just see out the patient object inside of it. And if you see out the patient object, it will give you the output as provided in the sample output, at least for a single line. So when you look at the driver.txt here, and you're like, oh man, this looks like a lot of extra work to get all this exactly in the same way, blah, blah, blah. The answer is, well, I did this again, and it took me an extra 5 minutes just of like retyping cout statements and stuff like that. You should not do that. You can literally just see out a patient. And so this is just see out of this patient, see out of this patient, see out of this patient. And at that point, you're like, oh, well, okay. See, my hope is that you'll learn from me, right? My lesson is read the project description before you do it, because obviously I did not read the whole project description before I did it, and I would say that caused about 70% of my additional work, was just not actually carefully reading. Anyway, okay. So let's get back to this class. So let's do binomial heaps for the last half hour. What am I doing? I want to do a binomial heap. Here it is. So remember that thing that everybody hated? So, and no one understood the point, and everyone was like, what's the point of these? And I was like, quiet, I don't want to tell you the point. What's the point? Why do we do this? No. So, here it is. Here's a B0, right? And remember, all you needed to know about the B0s, B1s, B2s was literally their form, not what they're used for yet. I'm just going to review for 2 minutes the form of all these trees. Don't worry about all these combinatorial terms. That was just for my amusement. So B0 is a single node. B1 is a structure like this. A B2 is basically two B1s, right, that are kind of linked together like this. So as the rightmost child of a B1 is another B1, that makes a B2. The rightmost child of a B2 is another B2, that'll make a B3. The rightmost child of a B3 is another B3. That makes a B4. And so finally, for absolutely no reason, we can make a B5, right? And you make a B5 by doing this. You say copy and then paste, and then you drag it until it is like this. And so, of course, it's going to be huge. And so the answer is that this is actually now, this is a... So this is a B4 here. This is a B4. And then you set the rightmost child here to point all the way out to this dude. And then you get to write render mathematics LaTeX. B5. It's a lot of work for a subscript, but I like it. Okay. Also, it gives you time to think. So here it is. Here's a B5. And you're like, well, that's a horrible looking thing. But whatever, who cares? It's a B5. Have any of you heard of the show Babylon 5? Good show. Okay. So, right, let us continue. So now we have to make a thing out of this, right? So basically the whole thing is, at this point, what you should be asking is, like, okay, got it. I know what B sub k's are. What's the point? Let me tell you the point, okay? So, let me tell you the point. The point is that we can make a heap out of this, and let me show you how to make a heap out of this. Okay? So let's do well, let's not do the visualization yet. Let's just do, let me get a circle, and let me just make a heap. So here's a heap, and let's insert a value. Let's say that this is going to be a, I don't know, is this a max or a min heap? I don't know. Good question. Let's make it a min heap. So let's put 20 in here. And so what we're going to do, so this is 20. And so now we're going to insert another element. Okay, so if you remember that this is a B0, and now we're going to insert another element. And let's insert an element called 17. Okay? And so remember that we're doing all of this in the context of min heapage. All right? And so the idea here is that what we're going to do is, the rule now, you can only have one bi for any particular I. Okay? So here we have run into a rule breaking where we have two B0s, right? But there's a way to fix this. And so the way to fix this is, so basically insertion will break this rule, but we can fix it. And so how? So what we do to fix it is that we merge BI's to make BI plus 1. Zzz, right? And so let me show you how to do this. So the easiest way to do it here is you would say, okay, I have 20 and I have 17. Who is the bottom and who is the top? So this is a min heap. So the top should be, let me just make a copy of this node so I have an extra node over here. So the top of this one should be 17 and the bottom should be 20. And so now, instead of having two B0s, I have a B1. And now I'm happy, right? I don't have a B0. This is just a spare node that I'm going to use for parts. So basically here, so now let's insert a new one. Let's insert, say, the node, let's say insert the value 3. There we go. That looks pretty centered. So let's insert 3. And now you ask yourself, is there a violation? And the answer is, well, I have a B0, I have a B1. There's no violation, right? No violation. Keep on keeping on. Right? Okay, so now let's insert another node. Let's insert 5. Here we go. And so what you get to do here is then you're like, well, now I have two B0s. So I'm going to make the one with the lesser value as the root, because that's how you do it. And then what we're going to do is we're going to see this come out. Oops. There we go. So now you say to yourself, all right, cool. So that fixed the B0 violation. But now we have a B1 violation, right? We can't have two B1s. So how do we fix that? So what we do is we look at it and we say, okay, you have the smallest value, so this is a min heap. So what I'm going to do is I'm going to make you the right child of you. So, and by you and you, I mean 3 is the parent now of 17, or 17 is the right child of 3. Okay? So, question. Is anyone who's following this, who hates this, who likes this, who understands this, you know, what's going on here? Tell me something. And so basically here, what we've made is a B2. So let me just get B2 here. And let me pull out a B1. And then let me pull a B0 if I can. That's right, it's a B2 now. And so the way that we store this as a data structure is actually as a vector of basically BI pointers, right? Okay, so let's insert a new node. Let's insert, say, I don't know, 13. Come on, help me. Why can't I click? Okay, let's insert 13. And then let's insert a new node. Let's insert, say, 28, right? 28 is a good number. And so remember what we're going to do. What we're going to do is when you try to insert, you see that the problem is that what you have is an extra B0. So we're going to throw it down here. Like a so. You're going to merge it. And then you're going to say to yourself, wait a second, this can't be in the B0 slot anymore. We have to move we have to promote it, right? Whenever you do a merge, you have to promote the thing to the next BI. So now if you insert a new node here, what are we going to do? Let's insert the node, say 8, okay? And so now that becomes the new B0. So this is an empty slot, so basically like this is a null pointer here, so we can just stick in this new node here. And then what we get to do, and now here's the exciting part, right? Is everyone ready? Everyone happy? Let us insert a new value. What value should we insert? It doesn't matter. 15, right? 15. It's a good value. No, let's insert 7. The reason why, okay, let me just show you why I want to insert, you'll see why I want to insert 7. Left and right child visualization. This is just kind of how they're drawn in textbooks. Also, the children of nodes are actually vectors of children. So, and you'll see that in just a second. So if we insert 7 now, like what happens when we insert 7? So when we insert 7, what we're going to do is we're going to say, okay, 7 has to compare to 8. 7 beats 8 in the sense that it's less. So it becomes the parent, and this one becomes the child, like this. But then you say, wait a second, we're still in trouble. Because now we wanted to promote something into the B1 slot, but we couldn't do it because there's something already in the B1 slot. So what do? We have to basically make this one, we take this B1 and we make it the right child. And why do we do that? We do that because 7 beats 13, so it's going to go in here. The page for this, I don't know what that means. You mean in the textbook? I guess I could try to pull it up in the textbook. Let's see. Binomial Heap. Is it in here? Guess what? It's not in the textbook. I'll try to get you some notes on it. Let's see if there's any good notes that we can just find on the internet really quick. No. Yeah, I did a search. It's not in there. Let's see if this is okay. Anyway, I'll find you some notes on it. Okay, but before we do that, let's just talk about the last thing that we want to do here, right? So we say 3 and 7. So 3 beats 7 because 3 is it's a min heap. And so here what we're going to do is we're going to insert. There we go. So there you go. That is basically as much of this as I want to do, at least manually. So now let's talk about deletion. Okay, so now you understand how to insert into a heap. And you see that it maintains the heap property because here 3 is less than 5, 17, and 7. 20 is less than 17, 8 is less than 7, 8 is bigger than 7, 13 is bigger than 7, 28 is bigger than 13. So the heap property, the min heap property, is maintained throughout the entire structure. So that's nice, right? So this maintains the min heap structure. That's nice. But now how do we do the other operation in a heap, which is delete? Right, so let's copy this and then let's delete. So what has to happen when you delete is that you're going to, I guess, ungroup this. And so this is going to be the node that goes because, and why is it going to be the node that goes? It's the minimum in the heap, so it's the one that's getting deleted. So that one gets deleted. And then the question is, what do we do here? And then what you see here is actually that we have a B0, we have a B1, and we have a B2. Nice, right? Okay, so let me show you now what happens in the general case. So basically here, like, what if we delete it again? It's a B3, not a B2. Oh yeah, it is. There's nothing in the B2 slot. Or am I wrong? That one's a B3. I guess I just didn't copy paste a B3 here. There we go. So now what? So now, if we delete min again, so we're going to take this one. This one will be the next one that we'll pull out. And you notice that nothing else has to happen, right? And so how do we know that this one was the minimum? Is it because it's in the B0 slot? The answer is actually no. The answer is that in order to find the minimum, you have to scan each one of the parents. You have to say, are you the minimum? Are you the minimum? Are you the minimum? And because this could have technically been 4 here and not 7. But it's 7 and not 4, so basically when we delete the minimum, here it comes. So we get 3 and then 5. So now what happens when we delete the next minimum? So let's delete the next one. So now 7 comes out. And we have a B0, which we're going to shift back here. And then we have a B1 that we have to merge here. So then basically the idea here is that you have two B1s. You can't have that. So in order to fix that, you just make this one the right child, and there. So basically everything in a binomial heap, so delete min and insert are both merge operations in a binomial heap. Here's the other advantage of a binomial heap. So there's a free merge heap operation that comes with it, right? So if we wanted to do is merge two heaps, then like if you had two binomial heaps, you could merge them. Let's just take, for example, say, let's take this whole thing. So if we had this as our heap now, and we wanted to merge it with something else, some other heap, then we would just follow the standard rules, right? So let's say that we wanted to merge it with something that was like, let's take a B1. Maybe we can find that somewhere. Is it like a linked list of heaps? Yeah, you can store it. You can store it as a linked list. So let's change these values. So let's say that this is 8, and let's say that this is 15, and then let's merge it with another one that's, say, let's put the minimum here. So let's say this is 2. I guess the rest of the structure doesn't really matter, as we're only changing the parents, and then maybe we'll merge it with another B3. And so this B3 will have a 5 as its root. So let's just do that. Yeah, I guess that'll work. Okay, so if your question is how the heck do I merge these things? The answer is that you do it in the same way that you do it when you have two general heaps. Or it's the same way you do it for the deletion algorithm. And so basically the idea here is that, let's see if I can, why can't I grab this? Oh, Lord. Ungroup. There we go. Okay, there we are. So basically the merge operation basically goes like this. What it does is it says, if you have two BIs, merge them. If not, pick the BI and stick it in the slot. So for instance, the answer to this thing here is going to be that there's only one B0, so we just take that. There's only one B1 here, so we take that. There's two B2s here, so we're going to have to merge it into a B3. And so the way to do that is that you say, okay, this one is going to be the parent because it's a min heap. And remember, so since we merged the two B2s, there's no B2. So B2 is empty here. B3 is going to be here. And so what we're going to have to do is take these two B2s. We're going to merge it into a B3. And this is how it's going to come out. And then finally, when we go up to the B3s, we're going to see that there's two of them. This one has a value of 3, and this one has a value of 5. And so we're going to have to merge them. And we had to merge them anyway because if we didn't merge them, then they would be sticking in the B3 slot. And even if there's only one of them, so that's the thing here. If there's only one of them, you have to merge that one with the B3 that just got carried up to that slot. And I'll explain what I mean by carried in just a second. So here we go. So 3 goes up top, and this one goes here. And then what we do is we join them, and then we have a B4. So this is the merging of the heaps operation. So let me explain this in another way. So let's look at binary addition. So what if we had the numbers, let's say 1101, and we had the numbers 1110, right? And we were going to add them. So what would we do if we had to add these two numbers? Right? So if we're going to add these two numbers, and remember this is binary here, so let's add these two numbers in binary. Yep. So this is the 0 column. So we're going to add them, and we're going to get 1. So what this tells us is that we know that there's going to be one B0 there. This and this add together. 1 plus 1 is 1. And then we get to here. 1 plus 1 is 0, right? Because we're in binary world. So 1 plus 1 is 0. Carry a 1, right? So the 1 gets carried. Let me just stick in a carry slot here. So this gets carried. And then here we see that 1 plus 1 plus 1 is actually 1 with another carry, right? And then here we just get a 1. So that's exactly what it is. So if I ever ask you, for instance, let's imagine that you only knew, right? Let's say that I tell you, you know, a 2 binomial, is deletion similar to subtraction? Yes, in a way. Yes, because what ends up happening, well, it kind of depends. Deletion is, actually, no. Deletion is like addition again, where what you do is once you remove the node, you add on, you merge with the rest of this thing. So it's kind of like addition again. Yeah, so actually everything is like addition. Because let me just show you what deletion looks like here. So remember, if you're going to delete a node here, like let's say that we're actually going to delete the min. And so if we delete the min, we search through all the B mins, and the one that's the minimum is 2, so we delete this one. And then what we do is we merge these two trees. So now this is binary addition again. And so what you do here is you would say, okay, here's two B0s, we add them together, we get a B1. Here are 2 B1s, we add them together, right, to get a B2. So the question is, what do you do in this case? So in general, I think the algorithm generally what it does is it will add these two together first and then promote this one to be a B1. So basically these two get added together here so that now we have a B2. And then you see this B2 is actually, it wanted to be in this B1 slot, but now that we've merged them, you can merge these two, which will then give you a B2. And then you are done. So this is kind of, and again, there's no B3 here, because a B3 would be, oh, I'm sorry, there's no B2 here. This is a B3. That's the right thing to say. Yes, so this is a B3. The B0 slot, the B2 slot is empty. So basically, delete min in this case was like adding what? It was like adding 1, 0, 0, 1, 1 to, what is it? 0, 0, 1, 1, 1. And the result is, and the result from that addition is basically what? It's 0 carry a 1. So 0 carry a 1. And then this one is 1 carry a 1. This one is 0 carry a 1. Then we get 1 carry nothing, because there we are. Then we get this 1 from the B4. And so that's what the result is. And so in a way, like, and we see that that matches because here we have no B0s. Basically the binary that I'm getting here. So the way I'm constructing the binary is reversed. So the way to think about it is that this is where it will. That's what B0 is going to. This one is B1. This one is, whoops. This one is B2. This one is B3, and this one is B4. So that's the process here. So basically what I'm doing is, yeah, and the reason, I mean, it would be nice to write it in reverse order, but the problem is that you kind of want to write it as a true binary number. If I wrote it backwards, then it would be like you would have to carry in the wrong direction. Yeah, so you see here, like, for instance, what am I doing? Where am I? Okay. So I'm not sure if I'll actually implement something like this in class. Maybe next time we'll talk about Fibonacci heaps, and maybe I'll do a little bit of binomial heap implementation. Yeah, because I'm a little perplexed. So I'm a little perplexed how easy it is to do in C++. I think I could generally do it relatively well in, but I don't know if I could do it in an hour, which would be too long, really. So, yeah. I mean, let's just see. Let's see if we can. And so, of course, what we're going to do, because I am way too lazy, so if we're going to do this, then what we need is or let's just call it children. Let's make this a struct to make it even easier to deal with. And then we will have int value. And then maybe our constructor will just set value to 0. Oh, maybe we'll even be nicer and say int new value. Right, and so this is what the node needs to look like. And then And maybe, you know what we could do? We could always have like an insert as, we could have and so maybe we'll have like a binomial heap node pointer and then an I. That way we can, what we can do is we can, there we go. That will allow us to insert as the whatever node. That way we can make sure that, and then we can have a get node, and then we can have an int I, and then we can say, this will probably make our implementation a bit easier. So if I is less than children.size, then we can return children at I, and then otherwise just return a null pointer. That way, what we can do is we know if there's nothing at that position. Like this is the real problem with this implementation, is that you just need, there's a lot of null pointers and stuff that you have to worry about because there's a lot of empty slots sometimes when you do these merging operations. So basically here what we can do is we can say, if I is bigger than or equal to children.size, then what we want to do is we want to just have like a for loop and then what we can do is we can just say children.pushback null pointer. See, look, this is coming, and then we can do children.pushback p node, and then otherwise else we could have just done children at I. See, I think this is going to make the implementation next time way more doable if I just do it this way, right? Because the idea here is that this is kind of taking care of the fact that there may not be a child at that position, or there may not be enough things in the vector, that kind of stuff. Because you see that, like, if you're trying to insert like a B4 into a binomial heap node that never had a B4 before, you'll just get like some problems with the array. And so here, the binomial heap itself, like what kind of things does the binomial heap do? It needs insert, right? Value. I guess we can do void. Maybe we can even, I'm not sure. And then what we need is basically, I think the trick is we can just have a kind of, yeah, let's do it this way. So let's have a, so binomial heap node pointer, but the root won't have anything in it. I'm just using it for its children array. And then we need an insert. We need a int get min, an int remove min, and then we need a merge with another binomial heap. And then, so we need a merge, and what else do we need? Maybe a destructor of some kind. Well, let's just do the destructing in the, we can actually do the destructing here. I think that's probably the smartest way to do it. And And then what we can do is just like delete this might actually make the implementation possible next time. Okay, I think we can do it. And the only thing I might write before is I might write some display method. Let me try to code this up like tonight or tomorrow. The reason why is because I want it to be something where you can see. Insert as basically allows us to insert this node here as a BI. So what this is going to do here is it's going to insert and the reason why we need it is just because, like, what if we have to insert, for instance, like a B7 into a node that only has had a B2 before, and so we need to add a bunch of blank null pointer spaces so that we know that the thing at position 7 is actually a whatchamacallit. And then, of course, the only private method we really need is merge on I don't know. Do we even need a private method? Probably not. This might be all we need. Maybe. Well, let's just have a private method merge. And then that way we can, you know, make it easier. So this is basically the structure of a binomial heap class. And so I might code this up outside of your view, and then I'll code the rest of this up inside of your view so that you can actually see how the stuff works. The display method is going to be the least interesting thing anyway, so my feeling is just, you know, you shouldn't really care how the display works as long as it works. What you should care about is the rest of this stuff. All right, so that's all for today. We'll do this and then Fibonacci heaps next time. All right. Cool. That's all. We're done. Stick a fork in it.